So very good evening to one and all. So this talk is based on a recent work where we have done a phenomenological investigation of the two anomalies present, namely power suppression and lensing anomaly. So CMB anomalies are basically signature which depart from the predictions of the nearly standard scale invariant model, and the two anomalies which I will address is suppression of power at larger angular scales and lensing anomaly. So studying these anomalies are important because these may be the signals of physics which are beyond our standard lambda CDM. So this is the suppression of power which I am talking about. Like for low multiples, there is significant deviations from the prediction of the standard lambda CDM model, and this is the plot in the angular space. So in order to quantify the suppression of power which is observed at lower multiples, we have a quantity known as S half, and the value of S half observed by Planck is 1209, which is very much less than that of the predicted value by the lambda CDM model. And next anomaly is lensing anomaly. So the CMB photons which are traveling from the last scattering surface get weakly lensed because of the presence of the large scale structures, and the effect of lensing can be seen in the higher multiples as the smoothing of peaks. So WMAP team has introduced a parameter known as AL in order to check the consistency between the effect of smoothing observed at the larger angular scale, effect of smoothing observed at larger multiples, as well as with the effect of smoothing which can be derived from the lensing potential. So the Planck basically reports the value of AL to be greater than 1, which is more than 2 sigma away. So my aim is to investigate whether there is any primordial connection between these two anomalies, one where the effect can be seen at lower multiples and other where the effect can be seen at larger multiples. So we have basically used some phenomenological models, some extensions to our standard NSATs, that is SA plus beta model and SA plus alpha plus beta model, and the important property is these models are agnostic about power suppression. So this is the S half value which is tabulated. What you can see is for the model SA plus alpha plus beta, the value of S half observed is much less than that seen in SA model, and since the value of S half is low, we can say that power suppression is most in the SA plus alpha plus beta model. So we have investigated whether there is interconnection between these two anomalies, and what we have observed is in method 1 where we have analyzed or where we have constrained the value of AL using varying all model parameters, and in second method where we have fixed the value of alpha and beta to the marginalized mean value, what we have obtained is in both cases there is elevation of lensing anomaly, because as you can see the value of AL is closer to 1 in method 2, and in method 1 there is a slight increase of error bar which in turn lead to an elevation of lensing anomaly. So we have analyzed our significance of our models using AAC and BAC criterion, and we have calculated a term delta, which is the difference between the model which we consider with that of reference model. And what we have found is delta BAC, if you check, that indicates basically the data prefers a strong model, but here we have analyzed our result using the whole multiples. But if we concentrate on lower multiples, when we check only the local feature, since the power suppression is only a local feature, we need to restrict the data only to lower multiple cases. Then what we have observed is the value from the delta BAC, the SA plus beta and SA plus alpha plus beta models are favored. So we have also done the analysis using PR4 data with updated likelihoods. So this is the value of S half plotted and the departure of lensing parameter from 1. So in lensing anomaly, as can be seen, significantly reduced with the Hilly-Pop combination, even for the case of SA. And I want to stress the point that higher the amount of power suppression means lower the S half value, more consistent is the value of lensing parameter from 1. So we have investigated the ability of future CMB missions in constraining our models. So we have used ICO, CMB Bharat, as ICO have improved the polarization sensitivity much more than the Planck. We expect more tighter constraints on our model parameters. And for that we have done we have assumed two fiducial cosmology, like in one without suppression and one with suppression. And what we have obtained is the value of alpha and beta constrained as such that it rules out the null values by more than 4 sigma. So this is the summary. Thank you.
Thank you, Roshna, once again for finishing time. Questions? Yes, Sovik.
I just don't understand why you didn't use the high multiple polarization data.
Yeah, I have used it.
No, but you wrote just temperature, then low L and low E.
No. I have done with that also. See here.
That is for this one, but for lensing anomaly, you only show.
No. We have analyzed our result using even for polarization. I didn't show that here.
Okay.
So how are you using those AIC and BIC in this? Like, can you just go to that slide and...
This one, right? Yeah.
Yeah, so you have chi-square, you have delta AIC, delta BIC, and now...
Because from this judgment criteria, I have analyzed.
Yeah, that's okay, but how are you using it? Like, are you filtering out some models based on this, or?
Yeah, we from this delta BIC, we have analyzed that if we consider the whole data sets like from L equal to 2 to 2500, what we observe is basically delta BIC favors favors standard NSATS model. But we strongly believe that the power suppression which is seen is only at lower multiples. So hence we need to analyze only for the lower multiple data. Then we can say that delta BIC is strongly favoring SA plus beta model since it falls in this criteria, and it have a moderate preference for SA plus alpha plus beta model. This slightly increase of delta BIC is basically due to the increase of this new parameter beta.
Okay, so I'll discuss with you later because
Yeah, sure.
I want to use